Hey guys, so continuing on with what we can do with vectors, I just want to take us back to when we first started talking about adding and subtracting vectors. So here's our example 2a. If F1, right, our force vector 1, is 8 newtons east, and F2 is 5 newtons east, okay, we can draw this out, but hopefully we can see these are both going in the same direction, right, directly east. Or we could say positive, right, in the x direction. So technically what we're talking about here is our net force in some x direction. Okay, and what would end up happening here is these would add together and we would get a total of 13 newtons east, right? Or you can say positive 13 newtons. And as soon as you say that I'm talking about F net x, now I can start talking about positives and negatives because I'm saying we're on the x-axis, okay? And if we look at our second example, right, if F1 is 6 newtons south and F2 is 4 newtons north, now we're talking about F net in the y direction, right? There's no x components here. So one is going down 6 newtons and the other one is going up 4 newtons. So these two things, when you add them together, remember one of them is positive and one of them is negative. So you end up subtracting them. So we would get a net force of 2 newtons south, or you can say negative 2 newtons, because again, we've defined this as an F net y. And once we're on the y-axis, now we can start talking positives, negatives again. So what this illustrates is that we can add vectors easily if the vectors are on the same axis. We can add them algebraically, right? They add together or they subtract together. When they start going, right, when you have an x component and a y component, that's when you have to add them with trig and with, with Pythagorean theorem, right? It's not as simple as addition or algebraic. So what this is telling us is if we have two vectors that are not on the same axis, but we can break them down into their x and y component, then things become a little bit easier for us. So here we're going to have an example 2b. Okay, and we have this box. It's 5 kilograms. And we're going to have two forces that are pushing on this box. We have some force 1, push of 40 newtons, and it is 30 degrees, right, coming down 30 degrees like that. And then we have a second vector that's pushing on this box, right, pushing up and to the right, whereas this one, the first one, is pushing down and to the right. We're going to call this F2, pushing at 20 newtons. And this one is at 15 degrees, right? So when I'm looking at this, I have two different, the tail of these vectors is each an origin to help us figure out what the degree that it's getting pushed at, right? We're drawing out some horizontal, right, dashed horizontal to give us a 30 degrees, which also helps us set up our triangles, okay? Now, if we think about adding these vectors in our head to tail way, you can say this one, I can never draw the straight line on this. Right, so we have F1 going this way. And then we have, and let's just make sure we get the angle going, 30 degrees. And then we have F2 going off this way at this angle, 15 degrees. And then if we want to draw the resultant vector, let's go with this pink. We get this F net right here, which we see is not going off at that 30 degrees. It's not going off at 15 degrees. It's going at some other angle that we would have to figure out. So right now, this is not a right triangle, so we cannot use Pythagorean theorem. But what ends up happening, let's get some different colors going here, get some deep purple, okay? So this first vector is going in some direction y down, and then, why not get fun with this, right, and some direction x, right, so let's call this f1x. Let's actually do a fun, oopsies, fun color here. And they look kind of the same. Don't mind me. Just trying to make sure that we have clear vectors as we're going. F1y, F1x. And then our second vector has some x component, F2x, and some y component up. Okay, so if I go down F1y over F1x over F2x and then up F2y, I end up at the same place as if I went from the beginning of F1 to the end of F2, right? So we cannot solve for this with just the initial vectors, so we have to break these vectors into their components. So we want to find f net x and f net y. And again, right, this is the important thing. We can add vectors really easily if they are on the same axis. So I see that I have f1x and f2x, and they are in the same direction, right? They're on the same axis, and they're going in the same direction, so they would add together. f1y is going down, f2y is going straight up, so those two things would subtract from each other. So if we set up our equations, we would get f1, let's do the x's first. So we get f1x here. Now we have to start thinking about our triangle, okay? And if this is 30 degrees, but I drew this triangle, right? I'd have to do 30 minus 9, or 90 minus 30. So technically that would be a 60-degree angle. But remember, the sine of 60 is the same thing as cosine of 30, right? So it doesn't matter what triangle you use, just as long as you're using the correct triangle. So here, if I do f1x, I'm doing the opposite, right? So this is going to be sine of 60 multiplied by f1, which is 40. And what we would get for that is 34.64 newtons, and this x is going in the positive direction. F2x is going to, so now looking at this, notice our angle is in the good spot there, right? We have the angle inside our triangle, so we're going to do, in this case, x is the adjacent side, so we're going to do cosine of 15 times f2, which is 20, and remember, I didn't actually write it over here for f2, but we have the value of f2 is 20 newtons, and this is coming from our problem. So cosine 15 times 20, again, this is a positive direction, 19.32 newtons. Okay, and those are the two things that are happening in the x direction. So they're both going positive. I'm going to add these together, and we get an f net x equal to 53.96 newtons. If we do the same stuff in the y, we can go f1y, and in this case that's the adjacent, so we're going to go cosine 60 times 40, and that is going to give us, now your calculator is going to say 20 newtons, but notice that it's going down, so it has to be negative. Super important, because when we add things together, it matters whether they are positive or negative. x2y is going to be, y is the opposite there, so we're going to do the sine of 15 times 20, and that gives us 5.18 newtons. and that one's going positive because it's going up. So again, we have to just assess what direction these things are going in. So when I add these together, I have a negative 20 plus of 5.18. So our F net y is equal to negative 14.82 newtons. Okay, now this doesn't actually answer our question because I haven't found the net F force. I found the net X and the net Y. So what we need to do is we need to now add these two together. And again, doesn't matter which way you go first, whether you go Y or X first. Let's go X first. So we're going to go 53.96 newtons. And remember, this was positive, so I mean I'm going in the positive direction. The Y component is negative, so I'm going to go down 14.82 newtons. And I know that this says negative and this, what I just wrote, doesn't, but for the fact that it's pointing downwards, I have taken care of the negative. And if we want to draw our net vector, we look like this. So now this is very similar to if in the first problem or the first video we did, if we know the X component and the Y component, what is the overall net force? We're doing the same exact thing. So F net, in order to solve, the magnitude is going to be Pythagorean theorem. We're going to take the square root of the size, 53.96 newtons, or newtons squared, plus 14.82 squared, and we get our magnitude there of 56 newtons. But we also need the direction, so we can get this angle, and we are going to do for the direction, again, I'm going to use the legs that we have, not the net force I just calculated. So again, we're going to use inverse tangent. Theta is equal to the inverse tangent of the opposite over the adjacent. And remember, that's SOHCAHTOA, that's how we remember it. You'll have access to these equations. And then this theta that I get is going to be, we can round it to 15 degrees. Okay, now I cannot leave this F net, I can't leave this as just 56 newtons 15 degrees, because remember, 15 degrees would get me up here, and I'm not in the first quadrant. I'm pointing in what we would establish as the fourth quadrant, so I can slap a negative 15 Newton, or 15 degrees there, because negative again is making us move in the negative direction. If you solved your triangle the other way and did the Y first, did this, and did this, I know it's not perfect, you would be getting this angle, which is 75, and remember, you can't just say negative 75, so you'd have to do east of south or something along those lines. So be careful how you're dictating, but make sure it's getting to the same spot. So this would be our final answer. Now, we actually haven't done physics on it yet, okay? So what we can do now is, now that I know the net force, a great question that can be asked is, what is the acceleration of the object? Okay, and now the only equation that we have with force and acceleration is F net equals ma. Right, now that we know the net force, we know 56, and if you go all the way to where we started, this thing had a mass of 5 kilograms, 5 kg. Acceleration. So solve here, and acceleration comes out to 11.2 meters per second squared, but that is just a magnitude. You need to also say the direction, and remember, the direction of the force is the direction of the acceleration. So if the net force is in the negative 15 degrees, then the acceleration is also in the negative 15 degrees. So remember, you need to have direction with acceleration, and it is not good enough to just do negatives and positives when you are not on the east-west or the north-south. If you're anywhere in between, you have to make sure that you are talking about your degree.